Good day and welcome to Lesson 4. In Lesson 4, we'll be looking at corrosion protection. My name is Engineer Sonny Ogboji, and I'll be taking you through issues related to corrosion. I want to start with a definition of corrosion. According to the International Union of Pure and Applied Chemistry in 2012, corrosion can be defined as an irreversible interfacial reaction of a material, which could be metal, could be ceramic, could be polymer, with its environment, which results in consumption of the material or in the dissolution of the material of a component of the environment. That's according to IUPAC. Corrosion occurs when a refined metal is naturally converted to a more stable form, such as its oxide, its hydroxide, or sulfide state, which leads to deterioration of the material. A metal corrodes when it reacts with another substance, such as oxygen, hydrogen, and an electric current, or even death and even bacteria. Corrosion can also happen when metals like steel are placed under too much stress, causing the material to crack. With that in the background, I want to look at the types of corrosion that we have. And basically, we have 5 major types of corrosion. We have pitting corrosion, crevice corrosion, intergranular corrosion, stress corrosion cracking, and galvanic corrosion. We'll be examining each of these briefly, and for a more comprehensive treatment, I refer you to the notes that are on the website to get more details. Now, the first one is pitting corrosion. This localized type of corrosion happens when a local anodic or cathodic point forms a corrosion cell with the surrounding surface. As the name implies, it takes the form of a pit that develops, or like a hole or cavity, which typically penetrates the material in a vertical direction down from the surface. If left unchecked, it continues to burrow down into the inner parts of the material. Other causes of pitting corrosion would include damage or a break in the oxide film, the protective coating, and the non-uniformities in the structure of the metal. Now, you know that metals might look plain, they might look uniform, they might look plain when you observe them with the ordinary eyes, but you subject them to more critical examination, you discover that there are lots of uniformities, and these uniformities could provide a very good opportunity for pitting corrosion to begin to take place. Then pitting corrosion is one of the most aggressive forms of corrosion and can be usually hard to predict, hard to detect, or even hard to characterize. The second kind of corrosion is crevice corrosion. Crevice corrosion occurs in areas where oxygen is restricted, such as where you have a bolt and washer, or a nut and washer arrangement. Areas under the washers or the bolt heads where you see a restriction in the amount of oxygen that flows in the environment. You have crevice corrosion happening in those spaces. And it usually results from a difference in the ion concentration between 2 areas of a metal. The stagnant microenvironment prevents circulation of oxygen, which in turn stops the repassivation and causes a buildup of stagnant solution, moving the pH balance away from neutral. Normally, as long as you can keep the pH value around 7 or in the region of 7, which is the neutral position, you will not have corrosion. But as it tends to move either towards the acidic axis or the base axis, alkaline axis, then you are playing into the zone where corrosion can easily take place. Crevice corrosion can take place at lower temperatures than pitting corrosion, but it can be minimized by proper joint design. If the joint is so designed that you eliminate or minimize areas that are where oxygen circulation is restricted, then you might have little to deal with in terms of crevice corrosion. The third one is intergranular corrosion. Intergranular corrosion occurs where impurities are present at the grain boundaries, which form during solidification of an alloy. Normally, alloys are first in molten form, and then they are allowed to cool and they solidify. In the solidification process, if impurities are not expelled, and in practical terms, it may be difficult to completely eliminate impurities, intergranular corrosion will tend to occur at those sites where the impurities are trapped in the grain boundaries. This kind of corrosion can also be caused by enrichment or depletion of an alloying element at the grain boundaries. And it occurs along or adjacent to the grains, affecting the mechanical properties of the metal, despite the bulk of the material being unaffected. The next kind of corrosion that I want to look at is the stress cracking corrosion. Stress cracking corrosion, or SCC, as the acronym. The acronym is SCC. It refers to the growth of cracks due to corrosive environment, which can lead to failure of ductile metals when subjected to tensile stress, particularly at high temperature. A ductile material is actually a material that you could draw and draw and draw further into a wire or whatever. Now, in the presence of stress corrosion cracking, as you attempt to draw, when you cross some limits, you see that the material fails. And high temperature provides a very good environment that can catalyze this stress corrosion and leading to ultimate failure. Now, it is more common among alloys than with pure metals, and is dependent on the specific chemical environment, whereby only small concentrations of active chemicals are required for catastrophic cracking. Then we have galvanic corrosion. And galvanic corrosion normally occurs where two different metals with physical or electrical contact are immersed in a common electrolyte, such as salt water. Salt water can be a very good electrolyte that encourages galvanic corrosion. Where you have two different metals immersed in salt water or any other common electrolyte, you're setting the stage for galvanic corrosion. Also, when a metal is exposed to different concentrations of electrolyte, we could have galvanic corrosion taking place. Where two metals are immersed together, they are known as the two metals that are immersed together, normally called the galvanic couple. The more active metal, which is the anode. Now, where you have a galvanic couple, the more active metal is called the anode, and the less active metal is called the cathode, or the more noble metal that is less in activity rate is called the cathode. And when you have this kind of arrangement where two different metals are immersed together, the more active metals tends to corrode faster than the more noble metal. The galvanic series will naturally help us to determine which metals corrode faster, and is useful when you want to use a metal as a sacrificial anode to protect a structure from corrosion, in which case the metal you want to use as sacrificial anode will be used as the outer layer, and that one can be given, is allowed to corrode, or if in case you cannot eliminate corrosion, that one wears out and corrodes fast, and then the actual metal that you want to save is preserved, and that one does not suffer any loss. Having looked at the types of corrosion, the next important thing for us is to look at the effects of corrosion on machine parts. And the effects of corrosion are very, very obvious. The first one is that there is damage to metallic parts of the equipment. Corrosion, we don't have issues with corrosion when we're talking about the polyvinyl chloride, plastic, wooden parts of our equipment or machine. But the metallic parts of our machines or equipment are the ones that pay the price when it comes to corrosion. Then secondly, there's a high risk of injury to employees and the general public. Why? Because a corroded metal or a corroded part of an equipment has lost integrity, has lost strength. It could easily fail, depending on how deep the corrosion has eaten into the material. It could fail, and if it fails, it could be injurious to humans, operators, and any other human beings that are within the vicinity of the failure or the accident. The third one is the loss of industrial equipment's time availability. When there's a failure or a breakdown, definitely that machine will not be available, either in part or as a whole. In part, depending on the part of the machine that has failed, and as a whole, if the scale of the failure or the criticality of the component that has failed is of the type that it will warrant shutting down of the entire equipment, then we have a situation where we have a loss of availability in terms of time. Then the next one is that it leads to a reduction in the overall value of a machine or equipment. From the aesthetic point of view, from other considerations, we discover that the value of the piece of equipment that is corroded goes down. It plummets seriously. Then corrosion has also caused issues like pipe blockages or damages to pumps in pumping and piping system, damages to valves. Sometimes you see, as a result of corrosion, a whole length of piping might have to be replaced. And this issue was very, very rampant when we were using more galvanized pipes and whatever. But with the advent and the use of PVC to replace most of the galvanized pipe application, the problem of corrosion has actually been reduced to a large extent. Then another effect of corrosion is damage associated with leaking gases or liquids. Corrosion can compromise the integrity of the pipes in which these gases and liquids flow through. And once compromised, we might have spots where leakage takes place. And at the point where the leakages take place, you see that corrosion rate is aggravated, leading to more serious damage and sometimes complete failure. Then contamination of fluids in pipes or vessels. And this is more critical, especially in applications like in the food industry, in the pharmaceutical industry, or industries where you cannot afford to compromise safety, where you don't want any form of contamination. Then corrosion becomes a serious issue that must be avoided. How do we control corrosion? Having looked at the effects of corrosion, how do we control corrosion? There are 5 primary methods of controlling corrosion, which are material selection, the use of coatings, the use of corrosion inhibitors, cathodic protection, and also design. Material selection, which is the first one we want to look at. Each material and alloy has unique and inherent corrosion behavior that can range from high resistance of noble metals, for example, gold, platinum, to low corrosion resistance of active metals. So you have noble metals at one end of the continuum and you have active metals at the other end of continuum. And normally we want to use metals that have the ability, that tend more towards the noble metals end of the continuum. Why? Because we want to minimize the rate of corrosion. The low corrosion resistance active metals could be sodium, magnesium, or other metals along that axis. Now, the corrosion resistance of a metal strongly depends on the environment to which it is exposed. That is the chemical composition, the temperature, the velocity prevalent around that particular environment. Consideration of corrosion resistance is often as important as in the selection process as the mechanical properties of the alloy. So you're not just going for strength, you're not just going to how rigid, you're not just going for the hardness and whatever, which are aspects of mechanical consideration, or you're looking at, okay, how resistant are they to corrosion, especially where that component is going to be exposed to the elements, to water vapor, to the atmosphere. There's no form of covering or lamination. Then you need to consider corrosion as you consider the mechanical properties. Then a common solution is to substitute an alloy with greater corrosion resistance for a corroded alloy. Once you introduce an alloy with greater corrosion resistance, then the environment is altered and you can have more stable operations. The next method of corrosion control is the use of coatings. Now, the intent is the same with either type of coating. You want to isolate the underlying metal from the corrosive media. The coating serves as a barrier. It separates the corrosive media from the metal, so that they don't come into contact. And if they come into contact, you know that the reaction that produces corrosion will be fast forwarded. You want to separate them so that they don't make any form of contact at all. Now, there could be different kinds of coatings. The first one is metallic coatings. The concept of applying a more noble metal coating on an active metal takes advantage of the greater corrosive resistance of the noble metal. An example of this system is galvanizing. Galvanized steel, for instance, the sacrificial zinc coating corrodes preferentially and protects the actual steel. So when you have galvanized steel, you see that you use zinc for a coating on it, and if at all corrosion is going to take place over time, it is the zinc that pays the price while the steel remains intact. Another form of coating is organic coatings. In addition to forming a barrier layer to stifle corrosion, the organic coating can contain corrosion inhibitors. And there are many organic coating formulations out there in the market. All what they do is they provide a coating to make sure that your parent material is shielded from the environment, from the forces in the environment that tend to encourage corrosion. We can also have inorganic coatings. Inorganic coatings, examples include porcelain enamel, chemical settings, silicate cement linings, glass coatings, and linings, and other applications, which all serve as barrier coatings. Some ceramic coatings, such as carbides, silicates, and other materials, are used for wear resistance and heat resistant applications, respectively. Another method of corrosion control, which is in wide application, is cathodic protection. Cathodic protection suppresses the corrosion current that causes damage in a corrosion cell and forces the current to flow to the metal structure to be protected. Cathodic protection can be achieved by two application methods. There are two methods we can actually apply cathodic protection. The first is an impressed current system that uses a power source to force current from inert anodes to the structure to be protected. And the second one is a sacrificial anode system that uses active metal anodes, for example, zinc, magnesium, or other group 2 metals, which are connected to the structure to provide the cathodic protection current. So it's either you are using the impressed current or you are using the sacrificial anode system. Both of them are forms of cathodic protection. And a more practical way of controlling corrosion is by design. The application of rational design principles can eliminate many corrosion problems and greatly reduce the time and cost associated with corrosion maintenance, corrosion control, and repair of damages caused by corrosion. Corrosion, as we know, often occurs in dead spaces, like the crevice corrosion that we looked at, where the corrosive medium becomes more corrosive. These areas can be eliminated by design. As you are designing the machine, you try to make forecast, or you foresee what is going to happen when the machine is actually installed where it will be used, the environment, and all the dangers associated with corrosion that you foresee, you eliminate them as part of the design. So you design machines that will not even be susceptible in the first place before you talk of controlling this thing. Designing the components to operate at stress levels below the threshold stress. Now, every material has a threshold stress for cracking. When you design them to operate at stress levels, maximum stress levels that are still below the threshold stress, then they will never get to that point where cracking can occur. And by that, you have eliminated stress corrosion cracking. Then where you anticipate damages as a result of corrosion, you can design to provide for maximum interchangeability of critical components and standardization of components, which means that in your design, you make it very, very easy to easily change, easily replace these components The moment I notice that one is beginning to fail, I can easily replace it with another one. And by that, I control the corrosion, or I eliminate corrosion or minimize it. So, by way of a summary, under this lesson, we have looked at corrosion protection. We began by defining or looking at what is corrosion as defined by the International Union of Pure and Applied Chemistry in 2012. We have looked at the types of corrosion, which we said include pitting corrosion, crevice corrosion, intergranular corrosion, stress corrosion cracking, and galvanic corrosion. We examined each of these types of corrosion in details, and we looked at the effects of corrosion on machine parts. Then we examined about 5 methods of controlling corrosion, which include material selection, use of coatings, use of corrosion inhibitors, cathodic protection, and design as ways of reducing or eliminating corrosion. Thank you very much. That's the end of this lesson.